We're going to start by talking about the pigeonhole principle here today. So first, one thing I want to bring up is that we have all sorts of cats. You know, I got Miss Kitty here. Hello, Miss Kitty. And they love boxes. They love boxes. Miss Kitty loves boxes. Mochi the cat loves boxes. The point is they love getting in boxes. And they aren't the only cats that do. I have a whole crew over here. I got even Pusheen over here. They love getting in the boxes. So, for example, here I got a box here. Here's a box. There we go. So Miss Kitty went in the box. She likes being in this box. She's just ready, excited in here. So that also includes other cats, like Mochi the cat too. I don't know where Mochi is. Mochi might be having a nap. She might be staring at me somewhere randomly. I'm not quite sure. She has a tendency of staring at me like some sort of automaton. I don't quite know. But the point is that she's somewhere. But either way, we need Miss Kitty here for our helping us here. So when we put Miss Kitty in the box, now Miss Kitty, are you enjoying yourself in there? Yeah, she's enjoying herself. So keep in mind that when we have a box, this is a discrete object. Likewise, Miss Kitty is a discrete object too. Now, obviously, she's more than just an object, right? She's a lovely, lovely kitty, right? Now, I would like to know something about how many kitties can be in a box. Keep in mind, if I had Mochi the cat or say Pusheen can go in the box with Miss Kitty. And now there's two kitties in the box, right? Now, I could have another kitty. Let's say here's this kitty. I could put this kitty in this box as well. So now I have three kitties in the box. See? Right, Miss Kitty? Meow. So we could have three kitties in the box and so on. Now, what if I were... Now, this isn't terribly interesting in its own regard. Yeah, I know, Miss Kitty. I know. This is your box. I know. But what if I had more boxes? Say if I have two boxes. I would like to be able to say something about if I have a certain number of boxes or bins versus how many objects, say cats, how many cats do I have in a box? So see, Miss Kitty's decided she wants to go check out something else. But the point is, imagine that I have all of my cats and I'm going to allow them to get into each a box. They don't have to necessarily get in the same box. They may not necessarily even get in different, all distinct boxes. But I would like to be able to tell you something about how many cats are in some box, at least. What can I say? And this brings me to the pigeonhole principle. So we're going to try proving this together. So this is what we call the pigeonhole principle. Pigeonhole principle. It works like this. So now suppose that we're given a positive integer n. So it's just the set of all integers, but only the positive ones. So I'm saying n is one of those. Suppose there are at least n objects. So that means n or more, like say n plus 1. And m bins. Where the number of objects is strictly more than the number of bins. Then there is a bin with at least two objects. In particular, you could say two objects, at least two objects. It's two or more. So what does this mean in the context of our kitties? That means that if I had three cats, for example, and two boxes, that means that at least one of the boxes has two cats in it. Just as an example. But we're going to prove this claim, and arguably I'm going to tell you that this is a really cute argument. And here's the game plan. Now, suppose that we didn't have this property in play. Suppose otherwise. So we're going to try to come up with what we call a contradiction. So if we're supposing these conditions, And if it's the case that there's a bin with at least 2 objects, suppose that isn't the case. Suppose that's not true. So assume otherwise. What does it mean then? What does it mean for it to be that there is no bin with at least 2 objects? What does that mean? What does it mean for there to be a bin with no, that can't have at least 2 objects? So what is the opposite of that? So what's the opposite of at least 2? So I'm not saying at most 2, I'm saying at most 1, right? It's going to be that each bin has to have no cats in it or no objects, or it has 1 cat in it or 1 object respectively, right? Because if otherwise, then there's some bin with at least 2 objects or 2 cats. So this is how we're going to lay out the argument. We're going to use contradiction. So we're going to see what happens when we set it up like this. So assume otherwise. So assume otherwise. If all the objects are placed into bins, then, as we just discussed, then it follows that every bin contains at most 1 object. Right, that's the game plan we have, right? That's what we've set out so far. Think about this. Think about this very carefully. If every bin contains at most 1 object, if that is the case, how many objects can be in bins? Then the total number of objects, and the total number of objects, and to be clear, I'm talking about the ones in the bins, right? Total number of objects is at most what? Well, there's at most 1 per bin, right? So it's going to be at most, and I have how many bins? Well, I have m of them, but notice that each one has an object in it, and m is strictly bigger than m, right? So it means that how many are in the bins? It's actually this. It's 1 per bin. It's 1 per bin, right? At most. Well, that's m, but this is less than n. But what does that mean then? There's not enough objects to go into the bins to actually characterize the number of objects there are, right? So that's a contradiction. So what does that mean then? Because remember, the total number of objects is going to be at least what? Well, it's n, right? But we've already established that if I assume this, then I'm not going to have enough spots for all of my objects, right? And this is why we reach the contradiction here. It's a pretty cute argument, right? The strategy we had was we assumed otherwise, then that means that each bin has at most 1 object. We count up how many objects at most could be in all of the bins, and we realized that there's not enough space in the bins to collect up all the objects. Hence our contradiction here. So this is one way we can prove the pigeonhole principle. Another thing I want to point out is some limitations, because the pigeonhole principle is an example of something that is non-constructive. It's a non-constructive property here. And the reason why I bring this up is because in computer science especially, you'll find that a lot of theorems tend to be constructive. For example, if I give you the proof of correctness of an algorithm, very often does the proof actually tell you how to build an answer. Not always, but most certainly almost always it does. So I must stress that even though this is a neat combinatorial argument and everything, it has some limitations. It's non-constructive, meaning it doesn't actually provide you an example of the thing for which there is, say, a bin with some object that has, some bin, I'm getting really excited here. It does not show you, for example, an example of where the bin would be that has at least 2 objects in it. So it's not constructive. It doesn't actually tell you an example. So what I'm saying is it does not tell you things like, 1, the bin with at least 2 objects. It can't tell you that. That's not what the Pigeonhole Principle says. It just says that there's some bin that has this, right? The second thing you need to be aware of is it doesn't actually tell you a lower bound on how many objects could be in any bin. It just says that some bin has at least 2 objects in it. It doesn't say that all the bins have at least 2 objects in it. So it does not tell you a lower bound for the number of bins. Sorry, not the number of bins, the number of objects, right? Number of objects in an arbitrary bin. So I'm getting really excited here. An arbitrary bin. It just says that remember, the Pigeonhole Principle says there's some bin with at least 2 objects. Like we talked about earlier, there could be a bin or a box, like we talked about, that doesn't have any cats in it, right? That's possible. They all could be in one of the boxes, right? They could all just be in one. Like, so for example, if I have my friend here, say if I only am considering, say these 2 cats, I got Pusheen and this cat. Suppose I only have, let's throw in another kitty. Let's get more kitties in here. Let's get this kitty here as well. Suppose I have 3 kitties and I have 2 boxes. What I could potentially have is that all the cats go into this one box. So I have 3 in one box, none in one box. So the Pigeonhole Principle only says that one of these boxes has at least 2 cats in it. That's all you could say here. Because this box has no cats in it. But this one has all 3 of them. So these are some important limitations I want to provide for you about this. But also, I want to tell you a little bit more about the Pigeonhole Principle and really what kind of the underlying, I don't want to bring up the dreaded M word, the mayonnaise, where exactly, like this concept, like why would you, like what, is there some formal way of talking about this other than objects and bins? And there's another kind of mathematical object for which we can describe the Pigeonhole Principle with. It's something we call a function. So, believe it or not, you can formally state the Pigeonhole Principle as well in terms of a function. So just as a reminder, a function, just like when we talked about our cats, each cat gets put in a box. Each one of these cats loves going in a box. So you can imagine that I could have a function that tells you, hey, look, this cat's going to go in this box. So each cat I give you, it assigns a box for that cat. So in the same way, you can think about this like a function too. So you imagine I give you some object in one finite set. So this is some finite set. And there's some function, we call it f, for example. It doesn't have to be called f, it could be called kazoo, for example. Doesn't matter really what its name is, as long as it's clear. And it outputs, in this case, some other element. And what it does is it sends it so it takes A and sends it to B. So, and that's some element of another finite set. So this is going to be the setup for how we would use the pigeonhole principle if we want to describe it in terms of functions. So just to make this a little easier for us to see, you can imagine this as the set A is your cats, and set B are the boxes. Just so you can see what we're talking about, suppose that I have 5 cats. I have 5 cats. I have 5 cats. I have 5 cats. Look at each of these kitties. They're so cute. They don't have whiskers, though. We don't have time for whiskers, nor places for their ears to go in. Okay? So we got 5 cats. I've got... And suppose that I have 4 boxes. So I have cats. I've got boxes. Now you can imagine that these cats are my objects. I'm going to call this capital O. It's not a 0. And I'm going to call my boxes capital B. So these are the set of boxes. This is a set of cats. So when I, for example, assign these cats, my lovely, lovely friends, meow, to a box. So when they all get together and they're like, hey guys, let's party, let's get into boxes. So they get in the boxes. How they decide to do this is some function, right? That's what I'm getting at. So let's suppose that, get this one here, that one there, and suppose that these 2 cats went into the same box. The function f, like I have defined over there, I could imagine this as f, or take some object over here, one of the cats. It tells me the box that cat OI gets into. And all the cats get into some box. So notice that I've just carefully characterized now our scenario that we had, but now as a function. So let's just kind of drop all the fluff, all the fun of this, the fun. So imagine I have now, like we had in our pictures before, I have 5 objects and I have 4 bins. And suppose, I think the third cat goes, third cat goes to the 3rd box, 4th cat goes to the 4th box, then the 5th cat goes to the 3rd box. So I have my objects, I got my bins. These are 2 finite sets. 2 finite sets. And the function I just described here is how the objects get assigned to the bins. So now do you see that actually our scenario is in fact it's described by a function. So now let's put this all together into the pigeonhole principle in terms of functions. So here's an alternative way to describe the pigeonhole principle now. So just to clarify, what I'm saying is that this is the same concept. There's an equivalency here. Sorry, I got a little excited there. So this is an alternative way of me saying the pigeonhole principle to you. So this is the alternative way of me describing it to you. So remember, in the pigeonhole principle, as I showed it to you, if there are more objects than there are bins, then there has to be at least some bin. There has to be at least one bin such that at least 2 objects appear in that bin. So what does that mean in terms of functions? Well, let's look at this picture, for example. This is just an example, right? So if I had 5 cats and 4 bins, you would tell me, yeah, there's some bin that has 2 cats in it or more, right? It has 2 or more cats in it. So what would that mean over here then? let's use our terminology from talking about functions. So remember, the number of objects is more than the number of bins. So let's think about this. And I must stress that if you characterize the pigeonhole principle like this, the proof is very similar. It's just in terms of functions instead. So now I'm going to say for every function f, from a finite set O, maybe I'll put a fancy little squiggle on that to make it a little easier to tell it's not a zero. A finite set O with n elements to a finite set B with m elements if n is strictly bigger than m, then f is not bijective. It's not bijective. You'll find that the argument that I gave you with objects and bins, it's the same idea. It's the same idea. It just has less of the function formalisms, okay? So that's the pigeonhole principle, everybody.